All right, here we go. Sorry I can't be there with you today, guys. I'm in the building. I just have to be out for a meeting. What do you notice on the screen? Well, first thing most people notice is number 21. Number 21 has a name. I don't know what his actual name is, but his math name, when you look at his height compared to the rest of the height on the team, is an outlier. The word outlier means some data point that is unusual compared to the other data in the set. And if you listed all of these people's heights, his height would be noticeably different. Therefore, he's an outlier. All right, so we can go and we can look at another example of this. If you were a full-size person and went into a kindergarten class, you would be the outlier for height. If we looked at our class every day, I am the outlier for age. If we listed everybody's ages, we'd have all of these numbers in the teens, 14s and 15s and 16s, and then one, well, we'll just say way older than that. Okay, so here's a story to get you to think about this and think about why this is important to know and understand what we're learning today. You just graduated from college. Awesome, congratulations. It's time to get a job. You look on a job finding website and you see this ad. Come work for us. We're a great company to work for and we pay our employees really well. Our average salary for the people in our company is $98,387. Wow. That sounds good, right? Man, if you went to work for a company whose average salary was almost $100,000, that sounds like a company to take the job for. Well, what if you knew more information? What if you were intelligent about how to deal with statistics and you dug in and you found this? Hey, there's actually in this company 31 people, okay? 10 people in the company make $25,000, 20 people make $40,000, and the one boss makes $2 million a year. And so when you do the mean calculation, it actually does end up to be $98,387. But you're not going to go this plus this plus this divided by 3 because you actually have 10 of these. So you have to go 25,000 plus 25,000 plus 25,000 plus 25,000 10 times. And then you go 40,000 plus 40,000 plus 40,000 plus 40,000 plus 40,000 20 times plus 2 million. And then you divide that all by 31. And so if you look at that, that looks like this. You would have to do that calculation. When you add them all up, you get this number right here, which is 3,050,000. When you divide that by 31, you get that number right there. You can accurately say that the average salary is $98,387. But what if you did this? What if you put the 20, and I just truncated the zeros. So it's 25,000, 25,000, 25,000, 25,000, so on and so forth. Here's the list of all 31 things. The median would be right here at 40, which means that if you actually were to calculate the median, you have $40,000. Now, what we have here is two measures of center. We have the measure of center called, as we know, the mean, and we have the measure of center called the median. Which of these is actually a more accurate, more honest, more trustworthy representation of what most people in this company make? I think it's obvious, right? It's the median. The median is a better measure of center for this data set than it is the mean. The mean implies that maybe some people actually make $98,000, but nobody even makes close to that. 30 out of the 31 people in this company make way less than $98,000, but a whole bunch of them, all 30 of those make around $40,000. And so this would be the more honest, more trustworthy, again, measure of center. All right. So that's what we're trying to figure out, is figure out what a weird number, right? What an unusual number. That was the boss. The boss's salary is unusual compared to the employees, and he is making a difference in some of these things. And that unusual number, called the outlier, has an effect on these different sorts of data measures in different ways. All right, so here's an example. If I gave you the data set 1, 2, 3, 4, 5, 6, 7. Ha, I said that wrong. I should have said 1, 2, 2, 4, 5, 6, 7. When you calculate the mean, you get 3.857. When you calculate the median, you get 4. Range is 6. IQR is 4. You can just trust me on that. I know you know how to do that. If I do the exact same data set, 1, 2, 2, 4, 5, 6, 7, 100, and I add in an outlier, it changes the mean. So the mean changed from 3.857 to 15.875. So was that a lot, a little, or not at all? I would say the mean changed a lot. So the 100 had a large impact on that. Okay, let's look at the median. The median went from 4 to 4.5. Did the median change a little, a lot, or not at all? It changed just a little. Sorry, I'm writing with my mouse. It's a little awkward. So the median changed just a little. It only went from 4 to 4.5. The range went from 6 to 99. So I think the range, it's safe to say, changed a lot. And then if we look at the IQR, we can see that it went from 4 to 4.5. And watch how efficient and lazy I'm going to be here. Oh, shoot, I moved the box instead of moving the words. Oh, shoot. We can take a little and just copy and paste it right down there. So having an outlier, it affected all of them, but it affected some of them more than others. The mean had a big change. The median had a little change. The range had a big change. The IQR had a little change. That is the math terminology we're trying to get then. When something changes a lot, we use the term sensitive. Okay. When something barely changes or doesn't change at all, we use the term resistant. And you can think about that. The mean really sensed the size of that number. It cared about the 100 and it gave us a big change because of it. So it was sensitive to it. When you put in the 100, the median barely noticed it. It was resistant to that outlier. And so you can see that happening here. If I gave you the set of numbers 1, 2, 3, 4, 5, 6, 7, and then I changed the 7 to 7 billion, if you were to add these all up, you would go 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 7, and that would give you 28. 28 divided by 7 would give you a mean. Remember, mean we say is X bar. That would give you a mean of 4. If you counted in from the outsides and found the middle number is also 4. So your median would be 4, right? So the mean and the median are both 4 on that one. Well, if you do the median on this one and you count in from the outsides, cross off your numbers as you go in, you notice that your median still stays as 4, right? Because the median didn't care what the size of this number was. It just cared that there was a number in that spot. However, when you do X bar now, you're going to go 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 7 billion. And let's see what that ends up being. So if I go 7 billion plus 6 plus 5 plus 4 plus 3 plus 2 plus 1, and I divide that by 7, the mean goes up to like 1 billion. So having this outlier here had a huge impact on the mean. It went from, I said 1 bit, that should have been bill, whatever. So the mean changed a lot, the median changed a little bit. Okay, I'm beating this into the ground, but it's because you need to know that. The mean is sensitive, the median is resistant, the range is sensitive, the IQR is resistant. All right, so this would be definitely something to pause the video and take out your toolkit and write in there. So when you say the mean is sensitive to outliers, that means that big outliers drag it up, small outliers drag it down. When we say the median is resistant to outliers, we're saying that big and small outliers barely affect it. When we say the IQR is resistant, big and small outliers barely affect it. And the range is sensitive, big and small outliers make it increase. Okay, that's it for this first video. We'll come back and do some actual tests of it on displays in the next video.